You know those days, right? You get home, you're just completely exhausted, and you think, man, I worked so hard today. But what if I told you that, according to the laws of physics, you might not have done any work at all? Yeah, it's a weird idea, so let's get into it.
Okay, just picture this for a second. A teacher is pushing against a solid brick wall. They're giving it everything they've got, muscles are straining, they're breaking a sweat. I mean, it sure feels like hard work. But in the world of physics, are they actually doing any?
Believe it or not, from a purely scientific standpoint, the answer is a big fat no. Zero work is being done on that wall. It sounds crazy, I know, but stick with me and you'll see exactly why that is. So to figure this all out, we've got to understand that physics basically borrowed the word work from our everyday language, but it gave it a super specific scientific definition. And spoiler alert, it has absolutely nothing to do with how tired you feel at the end of the day. And here it is, the official definition. It might look simple, but seriously, every single word here matters. For work to actually happen, a force has to act on something, and, this is the key, it has to cause that object to move, to be displaced. So how can we tell if work is really, truly being done? Well, luckily, there's a simple little checklist. I like to call them the 3 essential ingredients. And just like baking a cake, if you're missing even one, you're just not doing any work. Okay, let's break this down. First up, you need a force. You know, a push or a pull. Simple enough. Second, the object you're pushing or pulling has to actually move some distance. That's what we call displacement. And third, and this is the part you really got to remember, the force you applied has to be the reason the object moved. And this, right here, this is the secret sauce. It's the part that trips a lot of people up. It's not enough for a force to make something move. For work to be done, the direction of your push or pull has to be lined up with the direction of the movement. Getting this is a total game changer.
All right, so we've got our rules, right? There's got to be a force, it has to cause a displacement, and they have to be in the same direction. So, theory's over. Let's put our new checklist to the test with a few real-world examples.
So, let's circle all the way back to our tired teacher. Let's apply our rules. Is there a force? Yep, for sure, the teacher's pushing. But is there any displacement?
And there it is. The wall doesn't budge, not an inch. So ingredient number 2, displacement, is completely missing. That means no matter how much effort is spent, in physics, zero work is done on the wall.
Okay, next up, a book gets knocked off a table and falls to the floor. What do you think? Work or no work? Let's run it through our ingredient list.
Yes, this one is a definite yes. So what's the force? It's gravity, pulling the book down. Is there displacement? Yep, the book moves from the table to the ground. And are the force and displacement in the same direction? You bet. Gravity pulls down, the book moves down. Check, check, and check. All 3 ingredients are there.
All right, now for a classic physics brain teaser. You've got a waiter carrying a heavy tray, holding it steady over their head and walking straight across the room. This one is a little tricky, so think carefully about the direction of the force the waiter is using versus the direction the tray is actually moving. So here's the catch. The waiter is applying an upward force, right? They have to push up to counteract gravity and keep the tray from falling. But the tray is moving horizontally across the room. See the problem? The force is vertical, but the displacement is horizontal. They're at a 90-degree angle. Since that upward force isn't causing the forward motion, no work is done on the tray by the waiter.
Okay, last case study. Let's think about a rocket. It's firing its engines, it's speeding up, flying through the vacuum of space. Are we doing work here?
Absolutely. This is a perfect example of work. The rocket's engine creates a massive force by shooting hot gas out the back, and that force pushes the rocket forward. That forward push causes the rocket to be displaced. It moves through space. The force and the displacement are in the exact same direction. It's a textbook case.
So, now we're pretty good at spotting when work is being done. But how do we actually measure it? Put a number on it? Well, the good news is the math is about as simple as it gets.
And here it is. The formula is beautiful in its simplicity. Work equals force multiplied by distance. That's it. It perfectly mirrors our definition. You just take the amount of force you applied and multiply it by how far the object moved in that same direction. Simple and elegant.
And when we do that calculation, what do we call the answer? Well, the unit we use to measure work is the joule, and it's named after the physicist James Prescott Joule.
And the definition of a joule just ties everything together so perfectly.
1 joule is the amount of work you do when you apply a force of 1 newton, which is about the force it takes to lift an apple, and you move an object 1 meter. You can literally see the formula right there in the definition. Force times distance, Newton meter.
Okay, so why do we even care about this super strict definition? I mean, why does any of this matter? Well, it turns out this idea is the absolute foundation for understanding efficiency, which is a huge deal in everything from building engines to, well, our daily lives.
Just think about any machine, a car, a blender, even something as simple as a lever. There's one unbreakable law. You can never, ever get more work out of a machine than the work you put in. In the real world, things like friction act like a tax. They're always stealing some of your work input and wasting it as heat. So the giant puzzle for engineers is, how can we design things to minimize that tax and get the most useful work out for every bit of effort we put in?
And really, that's the big takeaway here. This definition of work gives us this incredibly powerful tool to analyze pretty much everything. It helps us see where effort is being wasted, like our waiter pushing up instead of forward, and how to make any system better to get the most bang for our buck. It's literally the science behind working smarter, not just harder. So, I'll leave you with one last little puzzle to think about. Imagine you lift a heavy box up onto a shelf. You definitely did work on it, right? But then you take that same box and put it right back down in the exact spot you started from. According to physics, over that entire round trip, what was the total amount of work you did on the box? Think about our definition of displacement. The answer just might surprise you.